Hi, good morning everybody. So, today we will continue with complex reactions. Last lecture was also on complex reactions. So, we will talk about some more aspects of complex reactions. Now, like we talked about consecutive reaction and competing reactions. Now, today we will talk about this pre-equilibria, then maybe unimolecular reactions, okay, and how to treat these complex reactions. So, there are various ways to treat these reactions, I mean theoretically. So, basically in treating with complex reactions, there are things that are to be taken into consideration. One is called the concept of rate determining step. That is the step that is an elementary step which determines the overall rate of the reaction. So, that is called the rate determining step. Another is the pre-equilibrium state, okay, and also another thing which is called the steady state approximation. So, we will take up these issues one after another. So, what is a rate determining step? Now, in short it is called RDS. So, a complex reaction, suppose we have a complex reaction of the form A to B to C. Now, of which this first step is rate constant is K1 and the last step is having the rate constant K2, and among these two steps the A to B step is the slower one and B to C state is the fast one, that is it occurs very fast, means it does not take time. So, this slow step is the bottleneck for the process. If the bottleneck is narrow, then if you think of flux going out of the bottle. So, if the bottleneck is reduced, I mean bottleneck diameter is reduced, then outgoing flow will be less. Okay. So, it does not really matter at what rate it is being that is inside is being filled up. Suppose there is an inlet and there is an outlet. So, inlet is having a say constant diameter and there is an outlet whose diameter can be varied. So, if you change the diameter of the outlet keeping the inlet diameter fixed for a bottle maybe having two openings. So, in that case this outgoing diameter is the determining factor for the overall output of the process. Okay. So, A to B to C, this is it is this first step is the slower one. So, it is called the rate determining step. Situation can be different, that is A to B is the fast and B to C is the slow or RDS. Okay. So, let us have an example that 2A plus B producing or giving rise to products, and if the mechanism of such a process is like A plus B giving rise to C. So, A plus B giving rise to C with rate constant K1, then C plus A with K2 giving rise to D, it is a slow step, then D with K3 giving some F, then F with K4 giving rise to product, both are fast. Okay. So, this step is the rate determining step. So, overall rate of reaction will depend on this particular step. Okay. So, this is an elementary step. So, this is there are 4 steps 1, 2, 3, 4, of which each and every one corresponds to one elementary step. So, this is one elementary step for which the rate, it is the slowest process. So, therefore, rate of formation of the product d dt of product for concentration of P is equal to K 2 C concentration of C into concentration of A into concentration of A. Therefore, elementary steps, in elementary steps number of species which are involved in this elementary step should come into the rate equation. Okay. So, this elementary step is a second order process, okay, or may be regarded as a bi-molecular process or bi species process. So, dCp dt is your K 2 Cc into Ca, being this being the the rate determining step. Now, what is the pre-equilibrium concept? Pre-equilibrium concept is that, like let us have the have some example that A plus B giving rise to C, but this is an equilibrium process. Okay. So, K 1 K minus 1 is the reverse rate constant and K 1 is the forward rate constant. So, this is the fast equilibrium. So, this equilibrium is established very fast. Then the C undergoes a further reaction with K 2 producing D, okay, and this is the slow, okay, slowest step. Okay. So, equilibrium constant for this particular step where the fast equilibrium has been established is your C C divided by C A into C B, of course, under dilute solution approximation, because if it is a concentrated solution, then you have to invoke the concept of activity. So, C C divided by C A into C B is K 1 divided by K minus 1 is equal to K C. It is a concentration equilibrium constant. So, rate of formation of your product d dt of C D will be K 2 times C C. Why K 2 times C C? Because in this particular elementary step, this product is formed with a slowest rate. That means, this is the rate determining step. So, kinetics of rate determining step is the deciding factor. So, rate equations should include this particular step, okay, because other steps are basically all on a sudden, it happens very fast. So, the whole process, that is the speed of the whole process will depend typically on this particular step. Therefore, d dt of C D is equal to K 2 into C C, K 2 times C C is equal to K 2, then C C is equal to, this gives you C C is equal to K C concentration equilibrium constant into C A C B. So, that is you just plug in this. So, K 2 into K C into C A into C B, okay, that is equal to K 2 into K 1 by K minus 1. This is equilibrium constant is this. So, you just plug in this over here equal to into C A into C B. Okay. So, this is a overall these three are constants, rate constants at a given temperature, as long as temperature is fixed. So, these three rate constants are constant, that is they do not change. Therefore, d C D dt is equal to a overall constant K into C A C B. So, although it is a fast equilibrium, but the overall rate will depend on the concentration of A and concentration of B. Okay. Now, let us have some concrete example, another example. Now, that is derive the rate law for the following reaction, of which there are 4 elementary steps, of which steps 1 and 2 are in equilibrium, that is, these are equilibrium steps, these two steps A and B, with equilibrium constant K 1 and K 2. Then third step with rate constant K 3 is the slowest one. So, therefore, this is your rate determining step, and D is the product formation, also this is fast. It is not mentioned, mean it is fast compared to this one. Okay. So, that means product formation rate, that is velocity, is equal to d product dt is equal to K 3 into E, K 3 into E, because because here this is the slowest step. So, this is your product. So, since this happens fast, therefore, your product formation will depend on this step. Therefore, d dt of product formation is nothing but K 3 into concentration of E, and concentration of C will be equal to K 1 into A B, that is from the equilibrium constant, and also E, concentration of E is equal to K 2 times C times D is equal to K 1 K 2 A B C. Therefore, velocity is equal to your K 3 K 1 K 2 A B and C. Okay. So, basically you see that it is a overall third order reaction, that is 3 concentration terms involved for this particular mechanism. Next, we will move on to steady state approximation. What is meant by steady state approximation? Now, again consider a 2-step process A to B to C, of which this is K 1, this is K 2, this is slow RDS and this is fast. So, that means it is produced, that is B is produced from this at a slower rate, and then it is depleted to give rise to C. So, steady state approximation means that as if at least for certain period of time the concentration of B does not change. Okay. Recall the consecutive reaction discussion, that it is like it is going like this and then it is decaying. So, this is the time when this is maximum. So, this concentration of B C B is maximum. Now, you see that in this vicinity of time the concentration of B is not changing a lot. That means, for this period of time you may think that the concentration of B is not changing, although if you think of the whole time course, then you will be seeing that at the end the product is primarily, I mean the reaction product is primarily composed of C, but for certain period of time the concentration of B is remaining constant. So, that means it remains steady with time, does not change. So, that is called the steady state approximation. So, d C B dt under steady state condition is equal to 0. That means, concentration of B is not changing with time. So, that is called your steady state approximation. Okay. So, consider a concrete reaction, say dinitrogen pentoxide into O5, giving rise to 2N2O5, giving rise to 2NO2 plus O2. So, it follows the following mechanism. Okay. The first step is that N2O5, this is an equilibrium, NO2 plus NO3, then NO2 plus NO3 with K2 giving rise to NO plus NO2 plus O2, then NO3 plus NO to give you NO2. So, we have to use, or we have to employ the concept of steady state approximation for two species. Okay. So, two species to find out the overall rate law. So, you see that this is one species and maybe this is another species for which we can apply the steady state approximation. So, NO and NO3. So, NO3 and NO. So, we have to apply steady state approximation for NO and NO3, okay, to find out or to derive out the rate law. Okay. So, steady state approximation means this is basically this approximation is applied to a species which are generally reactive. Okay. So, this is one reactive species and this is another reactive species, because actually this is an intermediate. They do not really have any existence in existence means at the end of reaction you do not find anything of this sort like NO3 and NO, but you will be getting NO2 and O2. Okay. So, that is why we have to apply, that is why we are applying steady state approximation to these two species. Okay. So, when we apply steady state approximation to this two species, then we get the following expressions: d dt of NO nitric oxide is equal to, so where to get it, you just try to find out where NO is produced and NO is maybe used up. So, here NO is produced and here NO is used up. So, NO is produced means, so rate of formation of NO2. Okay. So, that means K2 into, it is an elementary step. So, you can directly write these concentration terms into your rate equation. So, that means two concentration terms will be involved in this rate equation of production of NO. So, that means NO2 then NO3, and here this is used up, that is it is used up to produce some other product. Okay. So, that means here it should come with a negative sign because it is depleted. So, that means minus K3 into NO3. Okay. Okay. So, you put this equal to 0, that means you are invoking steady state approximation onto this, that is with time the concentration of NO does not change. In the same way, d dt of NO3. So, let us go back again, NO3. So, this NO3 is produced, okay, with a forward rate of K1 and it is used up, it is used up to get N2O5 back with K minus 1. That means, from this equation you should be having two terms, okay, K1 N2O5 minus K minus 1 NO2 NO3, K1 N2O5 minus K minus 1 NO2 NO3. Okay. So, K1 N2O5 minus K minus 1 NO2 NO3. Still other terms are there. So, NO3, so NO3 here it is again used up. So, therefore, it should come in a negative sign. So, minus, it is an elementary reaction. So, you can use directly the concentration terms NO2, NO3, because it is depleted, and here again NO3 is depleted, okay, with K3. So, minus K3 NO3 NO. Okay. So, there are 4 terms. So, you again put this to 0. Okay. So, this gives you concentration of NO to be equal to after simplification K2 by K3 NO2 and concentration of NO3, it is a reactive intermediate. Okay. So, that is equal to K1 N2O5. So, that means from these two simultaneous equations, from these two, that is these two simultaneous equations, okay, you should find out the concentration of NO and NO3. So, N2 K1 N2O5 divided by K minus 1 NO2 plus K2 NO2 plus K3 NO, and that gives you K1 N2O5 divided by K minus 1 NO2 plus 2K2 NO2. Okay. So, all these we have got as a result of application of steady state approximation. Therefore, rate of formation of O2, so ddt of O2, go back to, so rate of formation of O2. Okay. So, rate of formation of O2 is here, you see, rate of formation of O2 is here, is equal to K2 into concentration of NO2 and concentration of NO3. Okay. So, therefore, K2 NO2 concentration of NO3 is from here. Okay. Concentration of NO3 is from here means K1 O5 divided by K minus 1 NO2 plus 2 K2 NO2 times NO2. Okay. So, this gives you K2 K1 K minus 1 plus 2 K2 plus 2 K2 into O5. Okay. So, we can write d dt of O2 equal to K2 K minus 1 plus 2 K2 K1 O5. So, these together we can write as a constant K into O5. Okay. So, therefore, you see that rate of formation of O2 is proportional to the concentration of nitrogen pentoxide. Okay. So, so basically this from this, although you see that its stoichiometry is 2 N2O5 plus giving rise to 4 NO2 plus O2, but its rate of production of O2 is only first power of the concentration of N2O5. Next, we will move on to unimolecular reactions. Okay, so, this is called the unimolecular mechanism, which was proposed by Lindemann in 1921. So, how a bimolecular collision mechanism could lead to a first order overall rate law, that was first showed by Lindemann in 1921. Okay. So, the mechanism goes as like A plus A. So, it is a collision process, it is a bimolecular collision. Okay. Termolecular collision is again a phenomenon of least probability, but bimolecular collision is possible. Okay. That is, one molecule is reacting with another molecule of same kind, or one atom is reacting with another atom of same kind. It is called a bimolecular collision. So, A plus A. Okay. So, there is an equilibrium like a pre-equilibrium, K minus 1 A star plus A. Okay. So, it is energy, A star means it is energetically in a different state, energetically in an advantageous position to undergo reaction further to give you the product. So, energetically it is in favorable situation. Okay. So, basically collision means as a result of translation motion, and temperature is a measure of mean random translational kinetic energy. So, at a given temperature these molecules will have, in gas phase these molecules will have some translational energy, and they will move here and means to and fro inside the container. Okay. Sometime they will hit the wall, or maybe they will make collision. So, in that particular collision, means the collision which I am talking about, that is the collision between two molecules, these two molecules. So, this will lead to generation of an energetically excited, it may be vibrationally excited or maybe something else. So, excited molecule, of course, with one molecule of the same kind as the starting one, and then this A star will undergo a reaction to give you product, Okay. So, with rate constant K2. Okay. So, basically this is a quick equilibrium between unexcited and an excited unexcited case. So, these two are unstarred and one star, here one unstarred, and then this starred species is thought to be responsible for giving rise to the product. So, this is the concept of Lindemann, which was put forward in 1921, that in a bimolecular collision process overall first order reaction may result. It is a bimolecular gas phase, I mean it is a gas phase reaction. Okay. So, d dt of A star. So, rate of depletion of A, or maybe how time rate of change of A. Okay. So, it is basically formation, rate of formation is K1. So, since this is one elementary step, this is another elementary step. Okay. So, K1 into A square, because A is coming 2 times, that is why A square, minus K minus 1 A star into A, K minus 1 A star A, okay, minus, why minus? Because it is depleted. This side it is also depleted, and here also it is depleted. Okay. So, K2 A star. So, this is your this is your step for giving rise to the product. So, therefore, if you apply steady state approximation onto this reactive species, again we want to apply steady state approximation to this reactive species, then we have to put this to 0. Okay. So, therefore, that means this species is steady, that is the concentration of this species is steady with time. Therefore, concentration of A star is equal to K1 A square divided by K2 plus K minus 1 into A. Okay. So, reactive species concentration has got a square term in the numerator, and also there is a denominator term which is first power of A. Okay. So, the numerator has got a square dependence and denominator has got a to the power 1 dependence. So, it will give rise to some peculiar feature that I will talk about maybe in the next slide. So, your product formation d dt of product formation is equal to K2 into concentration of A star. So, you just plug in this over here, this gives rise to K2 times K1 into A square divided by K2 plus K minus 1 into A. Okay. So, recall this one, that your A plus A first equilibrium giving rise to A star plus A, then A star is undergoing a further reaction to give you product with rate constant K2. Now, we have to consider one aspect, that there is a time lag between the activation. So, this process is activation and decomposition step. So, as soon as it is produced, it does not undergo further reaction, but there is a time lag. That means, there is a time difference between these two steps. Okay. So, in that time, these activated molecules arrange themselves to a configuration. Configuration means in a definitive arrangement of atoms or molecule or parts of the molecule in such a way which is favorable for product formation. That means, they are rearranging themselves in a proper way. Okay? I mean, within the molecule, in this time lag, means time lag between your activation and product formation, what is happening, that these excited molecules, this A star molecule, okay, they are reorganizing themselves within the molecule such that it gives rise to products. But one point must be considered, that most of the activated molecules, these activated molecules, most of the activated molecules means most of the A star molecules so produced due to collision between A and A. So, these activated molecules, most of the activated molecules, they lose their energy through further collision, maybe collision with a second A molecule, but only a very little fraction of this overall A star have energy with suitable configuration to undergo reaction giving rise to product. So, that means say 100 A star molecules are produced as a result of collision, of which major fraction is getting deactivated, but maybe a little fraction, maybe 10 to 15% of the total population remains and giving rise to products. Okay. So, let us divide the whole course of the process into two regions. One is high pressure region, high pressure, and the other one is low pressure region. So, high pressure region means collisional deactivation is more likely. Why collisional deactivation is more likely? Because pressure high means these molecules are, these gaseous molecules are pressed from outside, so that they come close to each other, closer to each other. This means that they are coming close to each other means they have the larger probability, of being or having collision with another molecule, another excited molecule. Okay. So, that means collisional deactivation of A star is more likely than a unimolecular reaction. Okay. So, this is an unimolecular reaction. So, collisional deactivation, to give you A and A, is more likely because they are coming close to each other, as a result of high pressure. Okay. So, as a result of high pressure means they are close and therefore, they will collide often. Therefore, one A star molecule, suppose this is an A star molecule. So, the moment it collides with another common molecule, then its excitation is lost. So, it becomes like this, becomes a normal molecule. Okay. So, in high pressure region, collisional deactivation of A star is more likely than a unimolecular reaction, that is A star to product. Therefore, your K primed is reduced to K1 K2 divided by K minus 1, and the reaction is truly a fast order. I mean, this reaction becomes a fast order process. Okay. That is this one becomes important than this one. As I told you that this step is less likely compared to this step when pressure is high. That means you can neglect this term, and this gives rise to a constant of this form K1 K2 divided by K minus 1. What happens to low pressure? Now, for low pressure, so what is happening? Low pressure means this gas is rarefied. Gas is rarefied means they are put apart, these molecules are put apart from one another. That means collisional probability becomes less. So, what is happening that if there is a collision, that collision could be termed as the effective collision for the reaction to take place, because once this collision is happening under low pressure, then maybe this molecule is getting time to move around here and there, because it is not having any further collision to get deactivated. So, it is moving here and there, and during that time this molecule is rearranging internally to a proper configuration that is suitable for giving rise to product. That is why this bimolecular excitation process, this bimolecular excitation process under low pressure condition is the rate determining step. Okay. So, once it is formed, it has got a high probability of undergoing this reaction rather than collisional deactivation giving rise to A plus A, and under that condition your rate constant or the process becomes a second order. Okay. So, let us again try to understand it. A plus A giving rise to A star plus A with K1 K minus 1, then A star giving rise to product. At high pressures, A plus A collision is likely. So, deactivation is fast, unimolecular step is the slow step. So, this is the slowest step, okay, because this is the fast one. The A plus A under high pressure condition is the fast step, it occurs very fast. Therefore, at high pressure your effective concentration of A is large, and therefore, you can neglect K2 compared to K1 K minus 1 A, and therefore, the expression for the overall product formation rate is reduced to K1 K2 divided by K minus 1, which is nothing but equal to some constant times the concentration of A. That means, it is fast order with respect to A. Okay. So, under high pressure condition only one molecule is involved in the overall rate equation. Okay. At low pressure, A plus A star collision is unlikely. So, this collision is unlikely. So, it will get slow deactivation, the molecule or the starred molecule gets more time. Okay. So, that means it gets more time means this step is less compared to, I mean this expression, this has got less value compared to K2. Therefore, I mean this is less than K2 means you can neglect this. So, neglecting this, the rate of formation of the product is equal to becomes equal to K1 A square. So, this is basically a second order. Okay. So, under low pressure condition it is a second order, or it is a 2 molecule process. I mean 2 molecules are involved, 2 concentration terms are involved in the rate equation. So, you see a peculiar feature of such a kinetic scheme is that, I mean kinetic expression rate equation, that if you modulate these 2 terms, I mean modulate means if you can make this term predominate over here over this K2, or maybe if you can make this term predominate, I mean more than this term, then your kinetics or the overall rate equation becomes different. Under high pressure condition it is to the power 1 in A, and under low pressure condition it is square. Okay. Therefore, so what is the evidence that this is happening? So, again recall this expression, that dp dt is equal to K2 into A, dp dt is equal to K2 into A. Okay. So, that is K2 times K1 A square divided by K2 plus K minus 1 A. It is very simple, that I already told many times. So, you can write this overall rate expression like this, means in terms of the first power of A. Why I am writing in terms of first power? Because you see A to the power 1 it is A. So, at least it will be A to the power 1, this overall expression will be at least A to the power 1. That is why the minimum A to the power 1 term is written, and the rest may be coming into action depending on the pressure condition. So, therefore, remaining these terms like this K1 A divided I mean K2 K1 A divided by K2 plus K minus 1 A, okay, like this K2 K1 A divided by K2 plus K minus 1 A. Okay. So, this way K2 plus K minus 1 A. So, it is like K2 K1 A divided by K2 plus K minus 1 A. So, there should be a bracket over here, there should be a bracketed quantity. So, these two, it is not there is a typo, you should put a bracket over here like K2 plus K minus 1 A, these two terms should be within a bracket. So, if you inverse it, that is if you take 1 by K prime, then this will be your 1 by K1 A, because K2 K2 gets cancelled. So, 1 by K1 A, okay, and K minus 1 by K1 K2. Okay. So, you see that so this is a constant quantity, and this is a just 1 by A dependence. So, if we plot for certain if we plot like there are several examples. So, like if we plot 1 by K versus 1 by A, then it has been found that those reactions which follow this unimolecular mechanism, okay. So, for which it has been found that 1 by K versus 1 by A, it is like this, it follows like this. It is not truly a linear plot, it maintains linearity up to certain 1 by A value, and then it starts to deviate from linearity. Okay. So, this side is the high pressure side. So, pressure is increasing means 1 by A is decreasing. So, that means this side is low pressure side, this side is low pressure side, okay, this way, and high pressure this way. So, you see in low pressure region this is linear, this is linear, but in high pressure region it starts to deviate. So, that means we can say that truly this Lindemann mechanism is operative, okay, otherwise it should not have deviated and it should not show a pressure dependence, that is the rate constant should not have shown the pressure dependence. Okay. So, it is a test of Lindemann's unimolecular mechanism, whether it is operative or not. Now, how to find next is how to find the activation energy for a complex reaction. Again, look into Lindemann's mechanism, Lindemann mechanism, and also concentrate on to high pressure region, that in high pressure region your expression becomes dp dt is equal to some constant A, okay, which is nothing but K1 K2 divided by K minus 1 A. Okay. So, that means your rate constant, overall rate constant is K is equal to K1 K2 divided by K minus 1. Okay. So, if you recall Arrhenius equation, if you plug in the corresponding Arrhenius expression over here, then you can write for K1 you can write A1 exponential e to the power minus E A 1 by RT into A2 e to the power minus E A2 by RT divided by A minus 1. A minus 1 means for the, so pre exponential term for the back reaction, e to the power minus E A minus 1 by RT. So, that means it gives you A1 A2 divided by A minus 1 times e to the power minus E A1 plus E A2 minus E A minus 1 divided by RT. Okay. So, if you can write this as overall EA, then your expression reduces to, and also if you write this as overall A, then your K is equal to A into e to the power minus E A by RT. So, you can directly plug in this Arrhenius numbers into the overall rate expression. Okay. So, what we have learned today? Okay. So, let us try to sum up. Let us try to sum up that we are still in complex reaction, and treatment for the complex reaction is like you have to invoke the concept of rate determining step, that is the slowest of all the elementary steps involved in the mechanism. So, mechanism means your overall reaction can be divided into a number of elementary steps, or your overall reaction can be regarded as a combination of such and such elementary steps. So, each elementary step is a part of your mechanism. Okay. So, of which of these elementary steps, the step with lowest rate, that is the slowest rate, or the step which is the slowest one, is called the rate determining step. You can invoke the concept of pre-equilibrium, and also you have to invoke steady state approximation to find out the concentration of the reactive species reactive intermediate involved in the particular reaction, Okay. So, we have given example, and we have given one example where that this is your slowest step. So, overall rate of the reaction will depend on this one, that is this overall rate will depend on the concentration terms involved in this particular elementary step. It does not really matter whether whether this is still faster or it is little fast or like that, but this is the slowest one. So, therefore, this will take care of the overall rate of the process. Pre-equilibrium means before the reaction can take place, that is this is your final step to give you the product. So, there may be a very fast equilibrium to give you some intermediate, and then this intermediate is slowly used up to give you product. Okay. So, therefore, your overall rate will depend on the concentration of this term, and ultimately this will give you the concentration, overall rate is equal to Kca into Cb. Next is we have also employed the concept of steady state approximation, that if A to B to C is a sequential process, then B will have a steady concentration for certain period of time, and if you employ this steady state approximation, then you can say that dCb dt is equal to 0, and therefore using that you can find out the overall rate of process of a chemical process in terms of the concentration of your reactant. Then we talked about unimolecular mechanism. Unimolecular mechanism, that is that was shown by Lindemann in 1921, that A plus A giving rise to A star plus A. So, therefore, this A star is an excited species, and this excited means maybe different in energy state, maybe a little higher in energy compared to their starting material, and this excited molecule may undergo several processes, like it may just get deactivated, but by collision with A, or maybe by collision with wall, or maybe it will undergo a further reaction to give you product. Okay. So, further reaction means further reaction might require some rearrangement of the molecular geometry. Okay. So, and from this we arrived at the rate expression, that product formation rate is this, and under two pressure conditions, two pressure regime, one is high pressure, another is the low pressure regime. Okay. So, in high pressure regime, this expression becomes a first order with respect to concentration of A, and low pressure regime it becomes a second order with respect to concentration of A. And there is a test that if you plot 1 by K versus 1 by A, then you will be getting a linear dependence up to certain concentration or up to certain pressure region, but beyond that means if you go to the high pressure region, it deviates substantially from linearity. So, importance of this is that we have learned although it is a reaction between the same species, but it gives rise to product, but this product formation has got a peculiar dependence, and this was first put forward by Lindemann. And also we can plug in the expression arising out of this Arrhenius equation. Okay. So, this Arrhenius expression you can plug in to find out the overall activation energy of this process. Okay. So, this is a very interesting example of a complex, how to deal with these complex reactions, how to invoke this steady state approximation, pre-equilibrium, and maybe rate determining step in handling these complex reactions. So, we will continue to these complex reactions in the next lecture also, maybe next lecture, because it has got many variations, okay, and many examples are there. So, we should discuss them one after another, and then we will move on to theory of reaction rates. So, next day we will talk more about complex reactions. So, till then, goodbye.